This is 13.1/2, properties of fluids. Today we're going to talk about pressure, gas laws, thermal expansion, evaporation, and condensation. So fluids. A fluid is anything that takes the form of its container. So liquids, gases, and plasmas are considered fluids. Gas fills a container, spreading out evenly. So if I had like a high concentration of gas here, if I had like a gas cylinder or one of those like air cans with the compressed gas in it, and I let it open, that air is going to spread out evenly so that it has equal pressure here as it does over there. Liquids tend to spread out, but they're not going to spread out and fill the whole container, not three-dimensionally, more two-dimensionally almost, because they have less bonds. They have stronger bonds between them. They have less energy. So they're not vibrating around as much, so they're kind of stuck to each other a little bit. So they only fill the container as far as these bonds will let them stretch. If you think about a water droplet, and we draw a water droplet here, water has a very high surface tension because it is polar. So if we had a water droplet, you're going to actually see that it's kind of spherical as it sits on the table. But if you look at like rubbing alcohol, it's going to look more like that. Okay? It doesn't have, it's going to spread out. So if we have a bigger droplet, it's going to look kind of like that. Whereas water, the bigger the droplet, the more it's going to spread out. This is why you can put a lot of water droplets on a penny. I'm sure you've seen that test. And not a lot of rubbing alcohol, because rubbing alcohol has very low surface tension. Now, it is spherical when it stretches out like this, because if you look at a sphere and you have a molecule here, the outer edge, the radius is all the same. So this is going to put the least amount of stress on it. This is why water droplets are not square, because here is going to be longer than here. So this is going to have high stress and this will be lower stress. So it's going to try to even out these stresses and become more spherical. Thermal expansion. As things heat up, they expand. So if you had, I guess the best explanation is, you've seen the causeway, right? With the bridge, and it has these interlocking pieces. Well, those pieces, as they heat up, they actually expand. And when they cool down, they contract. So they need to make the cogs that fit into each other big enough so that when it does contract, that it doesn't fall apart. And when I was back home, we were having this problem where these bats were nesting up there, and we were having record temperatures, and it was expanding further than what the bridges were made for, so it was actually killing the bats. It was crushing them to death. So they were up there napping during the hot time, the heat of the day, so they were crushing them. Where here, we're used to those hot temperatures, so those bridges are used to, they were designed to expand that much. But it could be that they're maybe not designed for such really super low cold things. So let's say it dropped down to like -40, and they contracted so much that they were no longer touching, and then they crumbled and fell apart. That is not a huge concern, because we're not really going to reach -40, but maybe the next ice age. All right, the only exception to this is water. Water is a little weird because it's polar. So when it gets down between 4 and 0 degrees and it starts to freeze, instead of it being a liquid, right, it freezes into a solid, which most things will contract when they freeze. But with water, since it's polar, it actually expands, making it less dense than water, which is why ice is really special, because it will float because it's less dense. If you think of ice for any other type of substance, since it's going to contract, it would actually sink because it's getting denser. So it's good that water does this. It's a little strange because it doesn't follow the rest of the rules. But it does this because it is polar and turns into these ice crystals, so it takes up more space. But after 0 degrees, it starts to shrink again. So it'll get tinier and tinier and tinier. But this causes ice to float, which means the tops of the rivers are going to freeze, or the tops of your lakes are going to freeze before the bottom, which means it's going to protect and insulate all those critters that live down there. If it froze in the bottom first, it would kill them all. And then you wouldn't have life in your seas every time you come back from them. So it's good that it does this, it's just a little strange. All right, evaporation and condensation. We know what evaporation and condensation is, but we need to look at it in terms of energy. So evaporation, you have a puddle sitting on the ground, and it's a liquid form. Remember, it has heat, so they are vibrating, but they're not vibrating enough to escape, because they're vibrating just enough to have those liquid bonds. What's going to happen? The warmer air outside of it is going to cool, because the liquid is going to steal the energy from that warmer air. So it's going to cool the air around it, since it's stealing energy, and those liquid molecules, they steal enough energy, they're actually going to release into a gas. So they're going to phase change. So it's like boiling, sort of, since it's increasing its phase change, but it's not boiling because it's taking energy from the air, and it's doing it from the top down, where boiling heats from the bottom, creates a gas bubble, and that rises to the top. That would be what boiling is. This one is not that. It's just evaporation, where it takes the energy from the air, cools the air in order to escape. Still, it's stealing energy to escape. So evaporation is a cooling process. Condensation is the exact opposite of evaporation. If evaporation is a cooling process, condensation would be a warming process. Think of a cold bottle of water. It's going to steal energy from the air in order to warm up. So these molecules that are floating around in the air, they collide with the colder water bottle, and it takes that kinetic energy, it takes that heat from them, so they're going to get warmer since it's releasing that air. But it slows it down, and they slam into the side of your water bottle and condensate. They change phase. So since they're changing phase from the air, the gas, into a liquid, it is going to get colder since it's phasing down. Okay, sorry, it's going to get warmer. Evaporation steals energy as a cooling process. Condensation is a warming process. It's going to warm up because they're phase changing and releasing energy into the water bottle, which is going to get warmer because it's going to come to room temperature. That makes sense. Sorry guys, I gotta move on, I'm sorry. Okay, pressure. Pressure is the amount of force over the surface area. So, the force of this air, you can calculate how much force it has on the wall over the surface area. So if you do like the inside of this room, you'd be able to calculate it for the air. You could do it for a liquid. If you had like a square jar here, you take that area of the square, the surface area of it, and then the force of it, right, the weight of the water down on it. If you do it for a solid, you take the bottom of your shoe, right? However much you weigh divided by 2, because you only got, I'm just doing one shoe, so 1 foot. So half my weight onto the surface area of this shoe here. Think about this shoe versus a high heel shoe. It's the same force, but it's less surface area. So it would be like the toe and the heel. So less surface area means a higher pressure. So that's why girls are always complaining about why their feet hurt in those high heels, is because even though they don't weigh any more than they did, yesterday, the pressure is higher because they're standing on these little tiny areas. That's why guys don't complain about their feet hurting, because they got big feet, big shoes compared to us girls. This equation, usually when we do it in SI units, this is going to be newtons, this is going to be meters squared, and this will be pascals. I know in chemistry they use pascals or they use atmospheres. 1 atmosphere is 1 times 10 to the 5 pascals. A lot of the times they change pascals to kilopascals. And right now, this room temperature is at 1 atmosphere. This air right here. We live at about 1 atmosphere. Combined gas law. I'm sure you've seen this before. The combined gas law is Boyle's and Charlie's law put together. And this one works for any time you're trying to change from one situation to the other. So it's like, okay, I have a pressure, volume, and temperature here. If I change the pressure and the volume, what's the new temperature? Or if I keep the pressure the same and change the volume, what's the new temperature? This is really good for comparing first situations to second situations. With numbers. The first one up here is numbers. Now, if you're looking at just does it increase or decrease, you're just going to look at the simplified version of this law. This one only works for does it go up or down. You can't plug numbers into this one because it's not quite right. It's actually PV equals nRT, but PV equals T will just be good for increasing and decreasing. So we're going to play with this PV equals T. We're going to play the arrow game with it. I don't know if you guys remember the arrow game. But it says that if the two variables are on the same side, they're going to be opposite. And if they're on opposite sides, they're going to be the same. So we're going to play this couple little things. It says if volume is held constant. So I'm going to look at this one. I'm going to put a slash in volume. We're not interested in volume. It's not changing. It's not important. What happens to the temperature? So we're looking at temperature. If the pressure increases. Looking at the arrow game, what's going to happen to temperature? They're on opposite sides, so they have to be the same arrow. Make sense? Okay, if you don't like this version, set everything equal to 1. If pressure goes up to 2, what does temperature have to change to? 2. So if this goes up, that goes up. So do this a couple times, and then you'll see the arrow game is far superior. All right, let's look at if pressure is constant, what happens to the temperature if the volume increases? It's going to increase. All right. This time, we're going to keep temperature constant. What happens to the volume if the pressure increases? It's going to decrease. Same side, opposite arrows. Again, look at your math. If this is constant and our pressure goes up to 2, what does volume have to be in order to keep this side 1? It has to go down to 1/2. So if this goes up, that one goes down. One more. If temperature is constant, what happens to the pressure if the volume increases? It's going to go down. Decrease. Opposite. This stuff is really helpful for the SAT. Let's look at like y equals x over z cubed. The question would be, how does y vary with z? You remember these kind of questions from like ACT, SAT stuff, and you're like, I don't know. Okay, so what you're going to do is put it all in one line. Y equals z cubed equals x. Or y z cubed equals x. So, you know, it's just easier. You can play the arrow game with this one. So how does y go with z, right? How does y vary with z? Well, we don't care about x. That's not important. If y goes up, what happens to z? It's going to go down. So y is indirectly, you can just ignore my spelling today. Y is indirectly proportional to z by a factor of 3. Okay? I know you guys have seen this before and had no idea how to answer it. This is how you do it. So when they're opposite, they're indirectly, and when they're the same, they're directly. So this one, P is directly proportional with T. This one, P is indirectly proportional with V. If we did this, P is indirectly proportional with V by a factor of 2. I hope that helps you with your SAT stuff. All right, ideal gas law. I know you've seen this, PV equals nRT. For this equation to work, you need to watch your units. Your units are really important here. Pressure has to be in pascals. Volume has to be in meters cubed. N has to be in moles. And T has to be in Kelvin. This unit system will work when R is 8.31. There is another way to do this. I believe pressure ends up being in atmosphere, volumes is centimeters cubed, and temperature is in Celsius. It's like CGS units or something. They'll give you a different R for that. But for us, we're going to do it in SI units, so you want to make sure that your units are all on SI units. So that's the only real important part with this equation. I know you've seen this before. Is the ideal gas law. This one's used for one substance and no situational changes. So the previous one, you have some sort of situation and then you change it, you want to know how it changes. With numbers, it's PV over T equals PV over T. With, does it increase or decrease? You can just do a shortcut and do this. if it's just one situation with that gas, and you know pressure and volume and temperature, you want to know how much you have. It's like not changing at all. It's just this situation. What is the number? That's this equation. Guys, I got to move on. Here is, this table's in your book here, the center of the sun, 3 times 10 to the 16 pascals. Probably don't want to go there. The deepest ocean trenches, 1.1 times 10 to the 8, that'll kill you. Standard atmosphere, 1 times 10 to the 5, that's what we're at right now, so you can move your hand around and feel it. Your blood pressure, 1.6 times 10 to the 4, pretty close to 1. That's what's pumping through your veins. Mount Everest, 3 times 10 to the 4. The air is kind of thin up there. You'll pass out if you don't have oxygen. A little thin. And the best vacuum, 1 times 10 to the negative 13. You definitely want to be in some sort of astronaut suit there, because what happens is that when you open your lungs, actually even if you don't try to open your lungs, it's going to force all that air out of you. Because remember, air wants to fill the space that it's in. So when you're in a vacuum up in space, the air molecules are really far apart. They are up there. They're just really far apart. So all the air in your lungs is going to out, because it wants to fill the space that it's in. And it's so much less pressure here than it is inside your body that it's out. So you need a spacesuit to protect you from that. And your spacesuit needs to be kept at 1 atmosphere. Right. I don't know. It'll be in chapter 13, though. It should be in the one of the first 2 sections. All right, so we're going to do a practice. This is as hard as your questions will get, and the only difficult part here is the molar mass part and making sure everything else is in the proper units. So we have the average molar mass of some air, doesn't matter what the air is 15 grams a mole. And it says, what's the volume of 2 kilograms of the air at atmospheric pressure at 25 degrees Celsius? So what's this 15 grams a mole? Molar mass. It's actually not number of moles, because numbers of moles would just be moles. It even tells us average molar mass is grams per mole. So this one's molar mass, which I'm just going to call capital M here. Then we have 2 kilograms. What's that? That one's mass. So that one we're used to. And then we have 25 degrees Celsius. What's this? Good. What else does it give us? Say it louder. No, nothing? Atmospheric pressure. And atmospheric pressure is 1 atm. What's this? It's pressure. Pressure. Okay, what's wrong with these things? Not in the right units. So we need to change them. Celsius needs to be changed to Kelvin. So we're going to go plus 273, gives us 298 Kelvin. So that one's fixed. Atmospheric pressure is 1 times 10 to the 5 pascals. Kilograms is good. Well, sort of. Looking at this, so we have pressure is good, volume's what we're looking for. We don't have N. R is going to be 8.31, and we have temperature is good. So how do we get this thing, this N? It's number of moles, right? So we want something that has moles in it, but this is molar mass, not the number of moles. But it's molar mass, and we have the mass. So we need to use these things together to find out the number of moles. To do this, because this is grams per mole, we need to convert this into grams, which is kind of strange for us because we like things in kilograms. But because of the number that it's given, we need to put it into grams so we can get these moles. And then just look at your units. You're going to go, let's start with 2,000 grams. And we'll multiply it by 15 grams and then moles on top here. You see what I did? 15 grams per mole, 15 grams per mole with the mole on top. This will let your grams disappear, and you should just be left with moles. This is the hardest part of tonight's homework. So this will end up being N. So all we have to do now is plug it into our equation. We have 1 times 10 to the 5. We don't know, sorry, I almost said velocity. Volume. N, 1.33. R, 8.31. And T is going to be 298. So just watch those units, and that molar mass is a little tricky. It shouldn't be too bad. And I got 3.29. So the volume is going to be 3.29 meters cubed. All right, we got about 2 minutes left. I'm going to post your homework up here. And here it is. It'll be 1 through 22, no 10 or 13.